Kia ora koutou. This video is the first of 3 going over this year's end of topic complex numbers test. So in this quick prob video, I'm just going to do question 1, parts A, B, C, D and E. Feel free to skip through to the bits that you need, but make sure if you haven't got it absolutely perfect that you do watch those questions. So the first question is one where we're going to use the conjugate Serd to rationalize the Serd. We need to take this and write it into this form. So we're going to multiply numerator and denominator by 1 minus root 3, and now we're just expanding it out. So denominator first, we get 1 plus root 3 minus root 3, and then minus root 3 times root 3, which gives me minus 3. And in the numerator, we have 3 minus root 3 minus 3 root 3 plus 3. Okay, so what I'm doing there is I'm doing the 1 times all of that, and then take away the root 3 times all of that. Cleaning that up, we are left with 6 minus 4 root 3 over negative 2, which equals negative 3 plus 2 root 3. So that was an achieved question, not surprisingly. Right, the next one is one where it was really sad to see you not using the remainder theorem and doing a whole ton of unnecessary work that you could have used to think about, or you could use the time to think about those harder problems. When we've got a polynomial, we can find the remainder by evaluating the solution to the linear factor, right? So here, what we're going to do is set up p of x is equal to this cubic, and now we're going to substitute in x equals negative 1. And whatever pops out is the remainder when we divide by this. Now, lots of you did this by polynomial long division and did it really well, but just be on the lookout for remainder theorem questions. So now we're going to have take away 5. What have we got now? We're going to have minus 5 minus 2 plus 12. That gives me negative 8 plus 12, which is 4. So here the remainder is 4. Next one is an equation with surds. Now, we looked at these quite a bit in class. When we've got a surd on one side and just normal linear stuff on this side, all we have to do is to square both sides, and then we're going to rearrange. But the big thing with questions like this is that we must go back at the end and check that what looks like a solution really is a solution. Okay, so we're going to start here by squaring both sides. We get 1 minus 4x here, and we get x squared plus 10x plus 25 over here. Cleaning that up and solving the quadratic gives me x squared plus 14x plus 24, which factorizes really easily. And I'm about to lose I think something weird's happening with the OneNote tonight. Okay, let's see what we've got. We've got x plus 12 and x plus 2. So that gives me 2 supposed solutions. And we get down to here, and quite a few of you stopped at that point, and that was a U code if you got to there. But it's very easy to go back and check. But if we do go back and check, we need to kind of explain what we're doing at the end, right? So here, checking x equals negative 12, let's start on the left-hand side. Well, we get 1 plus 48, square root of that is the square root of 49, which is 7. Which is not equal to negative 12 plus 5, which is what we've got on the right-hand side. So x equals negative 12 is not valid or not a solution. So you really need to be communicating with something like that. And now we're going to go on and we're going to check x equals negative 2. And on the left-hand side, we get the square root of 1 plus 8, which is 3, and that is equal to negative 2 plus 5. So x equals negative 2 is a solution. Okay, so that was with merit if you checked the solutions and rejected one of them. Otherwise, just for this bit here, that was an achieved code. Right, let's look at this next one. Oops, okay, something weird is going on with the stylus tonight. Sorry about that. Hopefully it's coming back now. Yep, here we go. Right, one root of this equation is z equals 1 minus 2i. If p is a real number, find p in the other 2 roots. Now, the reason that we have to be told that p is a real number is that if p is real, then we can apply the conjugate root theorem, right? So by the conjugate root theorem, we know that z equals 1 plus 2i is a root. Then we can take this root and this one, and we can work them through into a quadratic term. So we have z minus 1 minus 2i and z minus 1 plus 2i. The easiest way to expand this is to rearrange it and think of it as z minus 1 plus 2i times z minus 1 minus 2i, just like we did in class. Cleaning this up, we get z minus 1 squared, then we get plus 2i times that, minus 2i times the same thing, which is why this all works, and then we have minus 4i squared. Expanding that gives me z squared minus 2z plus 1 plus 4. So the plus 1 coming from in here, so we get z squared minus 2z plus 5. Okay, so that's the first bit. So that's my quadratic factor found. And now what I have to do is to figure out what's p and what is my third root. So I know there are going to be 3 roots, right? So just moving over here, magically, we've got z cubed plus pz squared minus z plus 15. And we know now that that equals our quadratic term times something something. Well, the first something's got to be z, and then to get the 15 matching up, we have to have a plus 3 in here. So that means that we can now work out the last root. So z equals negative 3 is a root, and we also had to work out what p was. So to figure out what p is, we can just expand out the quadratic term. So on this side, we've got pz squared, and the quadratic term is coming from 2 places in here. We've got the z squared times 3 here, so 3z squared, and then we've got minus 2z squared here. There's nothing that's going to give me a quadratic with that plus 5. So that tells me that pz squared is equal to z squared, and p is just equal to 1. So there we go, that's that question done. Now that's a merit question, and that is a question pattern that comes up all the time in the standard, right? So it's well worth doing a few of those. There's one other way that you can do that. I'm going to just show you what that is now, but show you why you're more likely to, well, I think you're more likely to muck it up. And that is that you can take that solution and you can substitute in, and you'll get 1 minus 2i cubed plus p times 1 minus 2i squared minus 1 minus 2i plus 15, and then you can say that that equals 0 plus 0i, right? Because that's what 0 means when we're working with complex numbers. And then what would we do from there? Well, we'd expand all of this, and then we'd collect up the real bits and the imaginary bits, and we would get a value of p that way. But then you've still got a bit of work to do. So I don't recommend that method. If you've got questions about it, or you did it and it worked, happy to talk over email, or you can just leave me a comment. Okay, last question, which was the excellence question, was this one here. So we've got u is equal to 3 minus ki, and v is equal to negative 4 plus 2 ki. Then find k if arg of uv is equal to pi on 4. So what I should have been seeing in this question was a bunch of tiny little diagrams like this. Just some kind of sketch, because we didn't need to do a whole lot of stuff with tan inverse or anything. We just know that if the arg of a number is pi on 4, then it's sitting on a 45-degree angle out here. There, look, that's exactly 45 degrees. And the other thing we know that's important to get the E8 in this question is that if we've got an arg of pi on 4, then we're in this first quadrant here. So we need to have the real part and the imaginary part of this complex number uv both being positive. And what you'll see happens in this question is that we're going to get 2 solutions, but one of them turns up down here. So we need to chuck that one out. So let's first do the straightforward work of multiplying out uv and go from there. So uv is equal to 3 minus ki times negative 4 plus 2ki. Lots of little mistakes done in this expansion, so be careful. So it's negative 12 plus 4ki plus 6ki minus 2k squared I squared, right? So this is where there were a bunch of mistakes in there. A lot of you missed the k squared. That's okay, we've got till November. So we've got negative 12 here, and then this is plus 2k squared plus 10ki. Right, so we need the real part of uv to equal the imaginary part of uv, and both of these greater than 0. Negative 12 plus 2k squared has to equal 10k. 2k squared minus 10k minus 12 equals 0. Divide through by 2, k squared minus 5k minus 6 equals 0, and factorize. K times k, we want two numbers that times to negative 6 and have got a gap of 5, so it's going to be a 6 and a 1. That one's going to be the minus, so k minus 6 and k plus 1. That gives me k equals 6 or k equals negative 1. But we're not finished, because what we need to do is to check that we're in the first quadrant. So my complex number that I'm after, uv, is what we've got to go back to. So we need to just check that both bits of this are positive. So uv is equal to negative 12 plus 2k squared plus 10ki. And if k equals negative 1, what do we get? Well, uv is equal to negative 12 plus 2 minus 10i, which is negative 10 minus 10i, and that is sitting down here. Right, so k equals negative 1 is not a solution. Happily, when we put in k equals 6, we get uv is equal to here, negative 12 plus 2 times 36, which is 72, plus 60i, which is 60 plus 60i. And so that's sitting somewhere out here. And it does indeed have an argument of pi on 4. So there you go. That's the first question done. Make sure you go through your paper and just try and distinguish between silly but important arithmetic errors, which a lot of you still had, and conceptual lack of understanding, right? And then just make a wee list and use the old Delta book to target where your gaps are, and email me if you're not sure. Thanks for watching.